All right, so today we're going to continue talking about continuous functions on metric spaces. And you'll remember last class we proved this theorem here, which essentially gives us three different but equivalent ways to characterize continuous functions on a metric space. This first way, where we say that essentially around any point in the domain, for any point in the domain and for any epsilon greater than 0, we can find a delta greater than 0, so that whenever we have a point z that's within delta distance of the point x, the image of those 2 points are going to be within epsilon of each other in the codomain. So this is sort of the most close, or this is sort of the direct analog of the definition of continuity you may have seen in Math 290. There's also a way to characterize continuous functions in terms of sequences. And that characterization basically says whenever we have a sequence, a convergent sequence in the domain, which converges to a point that we'll call x, then if we basically look at the images of each of the sequence points, the f of x sub n's, that's going to form a convergent sequence in the codomain, and it's going to converge to the image of the limit in the codomain. Okay, so that's sort of a sequential way to define continuity for a function. And sort of the third way that we saw basically says that whenever we have an open set in the codomain, we can look at the preimage of that open set in the domain, and that should be open in the domain. So sort of put more concisely, the preimage of any open set should be open if our function is continuous. And indeed, those three things are equivalent as we showed last class, and whenever one of these equivalent conditions, and in fact all of them are true for a given function, we say that that function is continuous. Okay? So at the end of class, we define something which I think is worth restating, and that is a function f from x to y, where here x and y are both metric spaces, is called a homeomorphism if f is bijective and both f and f inverse are continuous. Okay, so homeomorphisms are sort of the correct notion of whenever we have what we're going to see that sort of when we talk about topological spaces, homeomorphisms are sort of the way that we think of two spaces as being equivalent. To a topologist, a pair of homeomorphic spaces are essentially indistinguishable. There's no way for a topologist to tell two homeomorphic spaces apart. Now, on the level of metric spaces, if you actually care about the distance between 2 points, then a homeomorphism, we can have two metric spaces that are homeomorphic, but where the function f doesn't preserve distances. So for example, you might have, well, maybe this is worth writing down. So note, homeomorphisms don't always preserve distances in metric spaces. Okay, so you could have 2 points that are like distance 1 apart, and in one of the metric spaces, and then maybe you have a homeomorphism to another metric space. So, maybe we have space x here and a space y here, and we have a point, say, little x and little z, and maybe these are distance 1 apart here. Maybe f is a homeomorphism, but maybe just, the point f of x and the point f of z, now they might be like distance 10 apart. Okay? So homeomorphisms don't preserve distances. They don't preserve sort of the metric exactly. Okay? But they do preserve something else that is important. Okay? And so to sort of see what this is kind of an important note. All right. So suppose we have let f be a homeomorphism from x to y. All right, so in particular, f is a bijection where both f and the inverse are continuous. So in particular, because f inverse is continuous, that tells me that if V is an open set in X, well, because f inverse is continuous, we know that any continuous function, whenever you have a continuous function, the preimage of open sets are open. So that means that the preimage of the set V under f inverse, which is just a fancy highfalutin way of saying f of V. So the preimage of V under the inverse function, so the pre-inverse of V under the inverse function, which is just f of V, since the inverse function is continuous and V was open, the preimage has to be open as well. Okay? So this is open in Y. And likewise, because f is continuous, if we have a set f of V, which is open in Y, well, then the preimage of f of V under the function f, which is just the set V, this is open in X. All right? So what does this tell us? Essentially, this tells us, if you combine these two statements, this tells us that V is open in X if and only if f of V is open in Y. All right? So this gives us a way to sort of think of homeomorphisms as being bijections. So homeomorphisms are bijections that preserve open sets. All right. In other words, they induce, if I have a homeomorphism from X to Y, it induces a one-to-one correspondence between the open sets in X and the open sets in Y. Every open set in X sort of corresponds uniquely to an open set in Y by just looking at its image, and vice versa. Okay? So although homeomorphisms don't preserve the metric, they do preserve the open sets that are defined by the metric. Okay? So we say that two metric spaces X comma D and Y comma rho are homeomorphic if there exists a homeomorphism F from X to Y. All right? And we think of homeomorphism spaces as essentially being spaces, metric spaces that are topologically the same. They have the same open sets. All right. So let's go ahead and see a few examples of homeomorphisms. Okay. So here's sort of example number one. Let's let X be the open interval from negative pi over 2 to pi over 2. And let's let Y be the real line. And here we're going to think of both with the usual metric all right, then we can find a homeomorphism from X to Y. So f is going to be a function from X to Y. And it's going to be given by f of X is just equal to tan X. All right. So claim this is a homeomorphism. Okay, and so to verify this, there are essentially three things we need to check. We need to check that f is a bijection. Right. So f is a bijection, and the inverse function from the reals to negative pi over 2 to pi over 2, the inverse function is just given by the arctan function. Okay. And so indeed f, so first of all, we've observed that f is a bijection, and I mean, obviously you might need to prove that. If you want to prove that, you can sort of use techniques, I guess, from Math 290 to do that. But once you go ahead and prove that f is indeed a bijection, you write down the inverse. You notice that, well, first of all, f of x equals tan x is continuous, and the inverse function equals arctan x is also continuous. Okay, so since both f of x and f inverse of x are continuous, this implies that f is a homeomorphism. And indeed that these two spaces are homeomorphic. All right. So if we want to draw a picture of this, we can. You know, on the one hand, we have our, on the one hand we have our original function, which takes the interval from negative pi over 2 to pi over 2. So this is negative pi over 2 to pi over 2. And the graph of this function, of course, just has these two asymptotes. Oops, that's not going to work. Okay, so that's the graph of f of x equals tan x. And then, of course, if we want to draw the graph of the inverse function, it's just the same thing, kind of, but on its side. I don't know, maybe this is, I guess you've all seen this graph before, but it's nice to draw a picture every once in a while. So this is what the arctan function looks like. All right, and so you can see, I mean, the way I think about it is what this function, what this function does is it takes this interval, f takes this interval, and essentially just stretches it so that it sort of spans all of the real numbers. Okay, so you're taking sort of this interval of finite length, this open interval of finite length, and you're stretching it out so that it sort of covers the entire real numbers in the y direction. Okay, but essentially this tells us that there's a way then we think of these two intervals, even though one is sort of finite length and one of them goes to infinity or sort of infinite length. We think of these two spaces, at least on the level of open sets, on the level of the topologies, which we'll talk about more later. We think of these two spaces as being the same, even though they're very different in terms of their metrics, right? In this space here, I can find pairs of points that are as far apart as I want, whereas in this space, I can only find at most points that are like distance pi apart. So these spaces are very different as metric spaces. Okay. Let's see another maybe slightly more weird example. Not super weird. So let's let this one, let's let x be the interval from 0 to 2 pi, and y is going to be just the unit circle. Again, both with the usual metrics. Let's let g be a function from 0 to 2 pi, in the interval 0 to 2 pi to s1. Let's let this be defined. Oops. Be defined by taking g of x equals cosine of x, comma sine of x. You can check that g is bijective and that g is continuous. Okay? So g, this function we've defined here, is bijective and it's continuous. So the question is g a homeomorphism? Okay? Well, because we've just checked, that because you can check that g is bijective and that g is continuous, really the only open part that you have to check to make sure that g is indeed a homeomorphism is whether the inverse of g is also continuous. Okay, so let's think about this function for a second. All right, what this function is doing essentially is it's taking the interval from 0 to 2 pi, and over here we have our unit circle. Maybe I'll draw it in red. So we have our unit circle S1, oops. And what this function is doing, what g is doing, is it's taking this interval here and starting at 0. When you plug in 0 into cosine and sine, you're just going to get 1 comma 0. So we're going to start at the point 1 comma 0, and as x increases, we're just essentially taking this interval and wrapping it around here. Okay. But at this endpoint here, we have an open endpoint, and so we can kind of think of that endpoint there as being open. Okay. So sort of on one side of the interval, we get a closed endpoint. On the other side, we get an open endpoint. And so what the inverse of g would be doing, the inverse of g is a nice well-defined function, right? Because it's a bijection, there's a well-defined inverse. What the inverse of g is doing is it's basically going to take this circle and it's going to cut it at this point, and it's going to then unroll it into an interval. Okay, so it's going to cut the circle at a point and then sort of unroll it into an interval. Okay, so the question is this g function, is this a continuous function? And maybe I'm going to make this a little bit bigger just because I can draw more on it. Okay, it's kind of nice lecturing on this because I can just like edit things however I want them to be edited. Okay, so I made that bigger for us. Okay. So the question is g inverse continuous? And the answer is no. Why does it have to be no? I mean, well, obviously, the line is not the same thing as a circle. So, I mean, I don't know. If you need anything more than that, I don't know what to tell you. But we can prove it. I'm just kidding. That was, my point is that obviously they shouldn't be homeomorphic because a line is not a circle. But why does this break the definition of continuity? So why is g not a continuous function? Well, if g were a continuous function, then it would mean that any open set I pick over here, its preimage should be preimage under g inverse, mind you, but its pre-inverse under g inverse should be open here. So for example, if I pick an open set like this, and I look at its preimage over here, Well, that's going to be open over here, no problem, okay? However, that's not going to be the case for all open sets I pick. So for example, consider this open set here. Okay. It doesn't look like an open set. This is not an open set in the reals. However, this is an open set in the interval from 0 to 2 pi. Okay. This is one of these relatively open sets. So it's open in this metric space, even though it doesn't look like it should be, but it is open because it's the intersection of a bigger open set on the reals with this smaller interval. So it's relatively open. And when we look at its preimage under the function g inverse, this preimage is going to look like, essentially on the real line, it's going to look like that. Okay, so one side is going to be open, but the other side is going to be closed. And in this space, in the space S1, an interval with one endpoint open and the other endpoint closed, that's not an open subset of S1. So here's an open set whose preimage is not open. Okay, and so that violates that definition of continuity. But we can actually also see it in terms of, for example, sequences, right? So if G inverse were to be continuous, it would tell, but the other definition of continuity says that if we have a sequence of points here that converges to some point x, then the corresponding sequence over here should also converge to some point f of x. But it's not too hard to see that we can find a sequence of points, so say starting here and sort of approaching this break point, okay? And if these things are converging to that point right there, then when we look at the image of this sequence, we're going to see a sequence of points that is sort of moving to the right and getting closer and closer to this endpoint. But notice the place where they converge over here is actually this point right here. So we have a sequence of points here that looks as though it should be converging, but the place that it's supposed to converge to is actually over here. And so that also shows that it's not continuous for that reason as well. So we can see sort of two reasons why it's not continuous. So notice. So notice we've proven that. So thus sort of we've observed. Thus G is not a homeomorphism. However, that's not enough to prove that this interval here and this circle here are not homeomorphic, right? To say that they're not homeomorphic means that there's no homeomorphism that exists at all. All that we've done is we've said that this one function that we think could be a homeomorphism actually isn't a homeomorphism. But that doesn't mean that there's not some other function out there that could be a homeomorphism. So in fact, to prove that they're not homeomorphic, we need some extra tools, okay? And we don't have those tools immediately available, but there are sort of, I mean, if you want to sort of try and think about how to do this, we don't quite have everything that we need in hand, but you know, if you look at one of these spaces, you'll notice that one of them is compact, and sorry, this one is not compact, whereas this one is compact. And it turns out that compactness is a property of spaces that is preserved under homeomorphisms. So that would be one way to show that there's no homeomorphism that exists at all, and that therefore these spaces are not homeomorphic. Okay, but we'll need to sort of prove that, you know, compactness is something that's preserved under topological spaces. So we will get there, but that's just sort of a hint as to how you might prove it. All right. So the next part that we're going to talk about, this is kind of a, I'm going to get a brand new page here because we're ready to start a new section. And in fact, it's kind of a shame that I'm not here in person, because this is where we actually define what topological spaces are. This is usually a very emotional part of the course, and there's lots of tears and congratulations, and I mean it sort of has a real celebratory nature when we cover this section normally. But we're going to do it remotely. That's okay. We can't, we'll have some other fun sections to talk about. So don't feel like you're getting cheated or robbed of the joy of talking about topological spaces. We'll have a lot of other great things to talk about. So essentially, up until this point in the course, we have been focusing on metric spaces, and metric spaces have this extra structure of a metric and a distance, which is a really nice structure to have if you have it, but there are a lot of things that behave kind of like metric spaces, either more so or less so, where there isn't actually a notion of distance that is sort of can naturally be defined. And in some places you can't define a notion of distance at all, really. So in these cases, we'd like to still be able to talk about things like compactness and continuity and convergence of sequences. Even though we don't have metrics, we'd like to have some maybe weaker structure that would still allow us to talk about continuity of functions, compactness, convergence of sequences, etc. And so to do this, we define a weaker structure, which is called a topology, which still allows us to do a lot of the things that we are used to doing in metric spaces. So without any further ado, let's jump in and define what we're talking about here. So let X be a set. Okay? A family of subsets, and I'm going to use script T to denote this family of subsets. So a family of subsets T of X. So in other words, T is just a subset of the power set of X. So it's just a family of sets special sets that we've picked out of X. This is called a topology on X if T satisfies the following axioms. Okay, so the first axiom is we want the whole space and we want the empty set both to be in this T set T. Okay. The second condition is any finite union, not finite union, silly me. So any union of sets in T is also in T. Okay, so whenever we take a bunch of sets in T and we take their union, the resulting set that we get should also be in T. So T is closed under unions. And part 3, any finite intersection of sets in T is also in T. All right. So again, we've got some, maybe a picture's worth, I don't know what my picture will be of, but so suppose we have a set X, okay? What we're doing here is we're basically picking out a bunch of sets that are going to be special, okay? So the first axiom sort of tells me that, hey, one of the sets that I have to pick out has to be the whole space. And I also have to, so the whole space has to be one of these special sets, and the empty set also has to be one of these special sets. But then I can also sort of specify other sets that are special, okay? And so I'm basically picking out a bunch of sets I'm picking out a bunch of subsets of X, where these subsets of X are going to be sort of my special sets. Okay, and once I've picked out all these subsets, I put them in a big bucket, and that big bucket is called T. Okay, and that that big bucket, which I've called T, is called a topology on my space. It's just a collection of subsets of X that are special, which satisfy these three properties. Okay? So, a topological space is a pair X, comma T, where X is a set and T is a topology on X. Now, these sets in T, if you look at these properties here, you'll remember perhaps that we proved when we were talking about metric spaces, we proved that open sets in a metric space satisfy exactly these three properties. And so in fact, these sets that are inside of T, we're going to call these sets open sets because these are sort of the special sets that we're considering to be open in our topology. So the sets in T are called open sets. Okay. And so this is supposed to sort of exactly mimic what we think of. If one of the examples we're going to see in a second is that metric spaces, open sets on metric spaces that we defined a week or so ago, they satisfy exactly these three properties, and therefore, if you take a metric space and you take all of the open sets that are defined by the metric, that is a topology. So this is sort of a generalization of the notion of a metric space, because we get a space, a set, and we get a bunch of open sets. Although we don't get a distance function, we do get the open sets that come from that distance function. So let's see an example. Our first sort of simplest example. So let X be any set, and let T be, so remember T has to be some collection of special sets inside of X, and it has to satisfy the three properties there. Well, the easiest way that we can satisfy the three properties there is we can just include the empty set, we can just include the empty set and the set X itself. Okay? Well, it's not too hard to check in that case that, well, does it satisfy this? Yes, of course. T contains the empty set and X itself. If I take the union of any elements in this set, we're still going to get an element in the set. So, I mean, really the only thing you can do is take the union of a bunch of empty sets and a bunch of X's, and when you take that union, you're just going to get X, which is one of the things in the set. And if you want to take finite intersections, you can take an intersection of a bunch of empty sets and X, and I guess as long as you have one empty set, you're going to get the empty set. And if you have no empty sets there, you're just going to get X. So it's closed under finite intersections, it's closed under unions, and it contains 0 in the empty set. So therefore, this is a topology. So then T is a topology on X. And we call this topology the indiscrete topology. On X. Okay, so this is kind of a boring set, or a boring topology, because the only, oops, something's weird, couldn't write there for a second. The only open sets in this topology are the empty set and the whole space. So not a super interesting topological space, but it is a topological space in and of itself. Satisfies those properties, so it's a topological space. Now, suppose we were like, that was a really boring example. Let's do an interesting example. Let's like add a bunch more open sets. So if you take that philosophy a little to the extreme, then you can kind of go sort of exactly in the other direction. So let X be a set again, and let, in this case, let T be the entire power set of X. Okay? So, in this first example, we said, well, hey, the bare minimum that we can include is the empty set in the whole space if we want it to satisfy those three properties. Here we're saying, well, let's throw everything. Let's include every single set inside of X and every single subset of X, and let's call all of those subsets open sets. So we should check sort of these three axioms up above. Well, is the empty set and the whole set included in T here? Well, of course, T includes all subsets, so it includes those two. If I take the union of any collection of subsets in T, do I get another subset in T? Well, again, every subset of X is in T, so any possible union I form is going to be inside of T. And likewise, any finite intersection I form using elements of T will also be in T, because, again, T is the power set. It contains everything. So, So then T is a topology on X, and we call this one called the discrete topology. We got really really creative in naming these things. Okay, and in this topology, in the discrete topology, every subset of X is open. All right, so you can kind of see we got, here you sort of include the bare minimum, the fewest open sets you can, and here you're basically including every open set that you possibly can. So they're kind of topologies that are on sort of opposite ends of the spectrum. Okay, but you can define these topologies for any set X. Another example, which shouldn't come as too much of a surprise to you, is if X comma D is a metric space, then the set of all open subsets of X in the metric D. So remember, if we have a metric on a set, then we can use that metric to define open balls, and we can use those open balls to define open sets. So if we do this on a metric space, we define open balls, we define open sets, then that collection of open sets satisfies those three defining properties of a topology, and therefore that collection of open sets is a topology on X. Okay? And this topology is called the metric topology on X. Okay. Now you should be a little bit careful. You might ask yourself, well, hey, is every topology a metric topology for some metric? And the answer to that question is no. There are lots of topologies that do not come from some metric. So it's maybe worth noting here. Note different metrics on X may induce different topologies. Oh, you know what? I should be a little bit more precise in my language here. So I said this topology is called the metric topology on X, or let's say the metric topology induced by D on X. Okay, so I want to sort of explicitly note the metric D, because it is possible that if I have two different metrics on my set X, I could get two different topologies. So the topology can depend on the metric you pick. So different metrics on X may induce different topologies on X. Now, sometimes you can pick two metrics and they induce the same topology. So, for example, on the first homework, there was that question that had you show that a set is open in the D1 metric if and only if it's open in the D infinity metric. And so what that shows you is it shows you that the D1 metric and the D infinity metric both induce the same topologies. Okay. However, that's not always the case. So sometimes you can have different metrics and they induce different topologies. Furthermore, not every topology on X comes from a metric. Okay? A topology on X that is induced by a metric is called metrizable. So if you have a topology and there is some metric that you can write down that induces that topology, then we say that topology is metrizable. Okay. So as an easy example of a metrizable topology, notice that the discrete topology on X is always metrizable using, well, let's think about this for a second. So remember we said that the discrete metric the discrete topology is this topology where every single subset of X is open. Can you think of a metric which when you look at the open sets gives you every set is open? So is there a metric that we spoke about where when you define the open sets, every subset of X ends up being open? Well, there was a metric, and it has a sort of very the name of it probably gives it away, but the discrete topology on X is always metrizable, and the metric you need to pick is the discrete metric. So remember, the discrete metric says that the distance between points X and Y is equal to 0 if X equals Y, and it's equal to 1 if X is not equal to Y. And so remember, this was this metric where all points are distance 1 apart. And so if you want to, you can just form a little open ball, say a ball of radius 1/2 around any point, and the only point, so if I have a little point Z and I look at the open ball of radius 1/2 around Z, the only point in that open ball is going to be the point Z itself. So in this discrete topology metric, every point is an open set. And since we can take arbitrary unions of open sets and end up with open sets, we can essentially construct any subset we want by just taking the unions of the corresponding points, and that'll give you an open set. Okay? So the discrete metric, the discrete topology is always metrizable, and the metric you want is the discrete metric. Let's maybe look at one more example here. Let's look at a topology that's not metrizable. So, example, well, the indiscrete topology is not metrizable if the number of points in your set is greater than or equal to 2. Okay? So for example, why is this the case? How do we see that this is not metrizable? For example, suppose our set X contains exactly 2 points, say 2 points A and B, and if D is any metric on X, then if we look at the open ball around the point A of radius 1/2 the distance from A to B, that set is just going to contain the point A. That open ball is just going to contain the point A. Okay? But remember that in the indiscrete topology, the only open sets we have are the empty set and the entire space itself. Okay? So thus, this open ball, which we'll call B, thus B is not open in the indiscrete topology. Okay? Even though it would be open in the metric topology. Induced by D. Okay, so so this is just an example of a topology, the indiscrete topology, that definitely does not come from a metric. All right, so we will continue on next class with some more examples, and talk about closed sets, talk about properties of closed sets, talk about some examples of things like the cofinite topology, neighborhoods, etc. So lots of more good stuff to come, and we will pick this all up on Wednesday.